Alright, welcome back. Hey, we got to think about how far in the future we want to worry about, alright? Not so much how far we want to worry about, I mean at least how far into the future are we going to trust these climate simulations? How far in the future, where are we going to stop on our path here as to like, we certainly can have trust, we can have faith in how these models are integrating this far out. And let's rather arbitrarily say the middle of the 21st century as being kind of our near-term climate change. That near-term climate change is a terminology that they use in the IPCC Fifth Assessment Report, okay? They mean like in the next couple of decades, what kind of climate changes can we see coming down the road towards us? And according to the IPCC AR5, just to take a actual quote from that part of the book right there, I think it's chapter 11, the projected change in global mean surface temperature will likely be in the range of 0.3 to 0.7 degrees Celsius. That is since the year 2000. So this is over and above the roughly 1 degree Celsius that we've had so far, depending on exactly how you measure it and so on. We're saying over and above that, in the next couple of decades, we can see something in that range. And notice that term medium confidence there, or we could say we have, the term will be likely. You might remember the IPCC report has defined all these terms. What do they mean by likely? What do they mean by probable? What do they mean by highly likely? Likely means that they believe that it is with between a 66 and 100% chance that the real value will be in that range. Okay, so there is a 66 to 100% chance that the actual global mean temperature change will be in that range. That's moderately confident results. Some of the models gave slightly higher, some gave slightly lower than that as far as their predictions. And I kind of like this scary plot right here that shows what the global mean temperature will look like out to the year 2050. Now this happens to all be model runs using the RCP 4.5 pathway. In other words, we're imposing 4.5 watts per square meter of anthropogenic climate radiative forcing on the model. And we're just letting it run. Now, these were runs, they were projecting forward from about the year 2008 or something like that. I'm not sure why they started with that particular year. And I like how this plot actually shows us the curves from all 42 members of the model. So 42 different research groups around the world downloaded the RCP 4.5 boundary conditions and ran the model out, and you could see the 42 different runs there, kind of like a spaghetti plot. It's not exactly the same thing as a spaghetti plot, but it has this kind of idea where you can get a sense of the range of the models. Notice none of the models saw the world getting cooler with that radiative forcing. But in fairness, there are some, there's a range as to some models show as much as like 2 degrees of warming after the year 2000 or 2008. I'm not quite sure what the reference is here. Relative to 2000, the 20-year average, 86 to 2005. Okay, so some show as much as like 2 degrees warming, although that seems to be a bit of an outlier by the year 2050. Whereas, in the range of like a little bit, right around 1 degree Celsius, maybe a little less, seems to be about where most of the models are going. Wow. You can see, for example, that all of them, okay, now here we see again another way of representing the results of this climate ensemble. We see for each of these 1, 2, 3, 4 years that they're showing us here, they are showing us error bars around a forecast, where that represents the different members of the model, the different members of the ensemble. So 42 different models made a forecast of the climate of the Earth in the year 2030. In black, that's the SRES A1B scenario. I don't remember exactly what that is. In blue, that is the 2.6 scenario. In light blue, that's the 4.5 one. And bright red, that is the 8.51, and so on. So you can get a sense of the range of the forecast over a range of different radiative forcings. What I want you to notice, if you go out to the year 2050, notice the dark blue set of bars right there. Okay, that's the most optimistic set of radiative forcings, only having 2.6 watts per square meter of anthropogenic radiative forcing. And that planet is a little bit cooler than like the red one there. See how the red bar there, that represents the 42 model runs using the 8.5 watt per square meter radiative forcing. So clearly adding more, and it's higher, right? So adding more radiative forcing made the planet warmer, okay? Even if we don't necessarily have huge confidence, that's a fairly big range of forecast there. The fact that they're all warmer, and though they get warmer, the more radiative forcing you're applying and so on, tells us something important about climate, that we're understanding these processes correctly. Okay? Let's see what those were global values. Let's actually look at some maps of what the models are saying here. Now, this is a figure that comes from your readings in the IPCC AR5. This is figure 11.10 if you want to go back and get a full resolution version of this for yourself here. And these are all plots using the RCP 4.5 scenario, which was the one that is kind of closest to the business as usual scenario, A1B. And this is showing warming over the next, to the year 2035 or something like that. And let's see here. Let's focus on the left panels here just to keep things a little simpler. The two left panels there are showing how the world's temperature will change in the northern winter season, and the bottom panel there is showing how temperature changes will happen in June, July, August, or whatever. Now, you can't really see the stippling very well on this low resolution version of the graph, but I'm going to give you a higher resolution one in just a second here. But stippling means that the little dots means that the changes are statistically significant. What do I mean by statistically significant in this context? That means that the 42 models that went into this ensemble were enough in agreement that we believe that that is a statistically significant result. We believe that the trend that it's showing there is correct. If you use cross-hatching on those same areas, it means there was too much variation between one model and another for that region. Even if it shows that on average there was warming or on average there was cooling, there was so much variation between the 42 model runs that we can't really say that we have all that high of confidence in the results. So like if I just zoom in the December, January, February figure up there on the top, this is how the planet's temperature will change between, the year 2010 or 2016 or something like that, and 2035. And so this is near-term climate change here. And first off, you'll notice that the darkest red colors are all up there in the Arctic. Okay, we've seen this before, that we've seen so far the greatest observed climate change, which we talked about in the first module of the course, had been up in the Arctic. And that's going to continue for the next few decades. And you can see here, we've got a lot of those stipples up there. This is all statistically significant. More or less all, if not all, of the models are showing a warming in that region. We have high confidence in those results. You can see that in general, actually, we have high confidence in the results. Almost the whole map is covered with those stipples. There's a few places where there's cross-hatching that says we can't necessarily draw statistical significance here because there was too big of a range within the range of models. Why was there all that climate change up there in the Arctic? This was about that ice albedo feedback. On surfaces that are covered with snow most, if not all of the year, most solar radiation is being reflected away. As you melt, because of the high albedo, as you melt snow cover and expose bare ocean or bare ground, more of the radiation from the sun is absorbed. So you get this feedback. Once you start melting the ice, it's much easier to warm that area because there's more exposed ocean, more exposed ground, and so on. It's the ice albedo feedback. In general, it's a little subtle on this particular diagram here to see that there are bigger changes in the temperature over land than there are over the oceans. It's actually a little hard to see it on that particular diagram. Let me just show you this one instead. This was a more regional set of plots. I forget the figure number in your book. But these are the same sort of thing. Again, these are temperature changes between, 2010 or 2016 or something and the mid-21st century. And you can see that the temperature changes, are much larger over the landmass and much less over the ocean. That is a common result in all the models. That's just because the land is easier to heat up than the ocean is. The land has a lower specific heat. The land can't cool by evaporation as efficiently as the ocean can. The land can't cool the surface by mixing the ocean the way the ocean can, right? The ocean can always cool the surface of the ocean by just bringing some colder water from below up to the top. Soil can't do that. Rocks can't do that. So in general, we would expect that there will be bigger temperature changes at the surface of the Earth over land than we would over the ocean. The models give us all kinds of information to help us understand what to expect in the near-term climate of the next few decades. For example, on this diagram here, we're talking about how common the warmest days are. Now, the measure that they're using here is how often does it happen that the day is warmer than 90% of the days were in the past. Obviously, that's on a certain calendar day, right? So, like, if today is March 16th, then what they're saying is we have a large sample already of how many March 16ths we've had. Are you warmer than 90% of the March 16ths were? Tomorrow, then when the model simulates March 17th, is the climate warmer than 90% of the March 17ths were? If there was no climate change at all, this would be a solid line across this diagram here right at 10. Because 10% of the days should be warmer than 90% of the days, right? But as the climate warms, warm days become there is an exceedance here. There is we experience more days where the temperature is warmer than it was 90% of the time. So like in these different RCP pathways here, you can see that even under the very mild warming of RCP 2.5, we end up with about 25 to 30% of the days are warmer than 90% of the days were before, right? We have about 3 times as many warm days as we did before the anthropogenic changes. Well, it's actually with respect to 1960, there already were some anthropogenic changes by then. And of course, if you go all the way out to the red curve here, RCP 8.5, or by the year 2100 or 28, whatever, I forget what days these go, I guess like to 2080, let's just say, almost 60% of the days in the model were warmer than all but those last 10% of the days in the past. In other words, the warm days become very, very much more common. Okay, well that's probably not a huge shock. Back in Module 1 when we learned about observations of climate, we also learned in that module that there was warm days were becoming more common. We learned at that time too that cold days were actually becoming less common. It isn't like the distribution of temperatures is getting wider, it's shifting to the right. So as a consequence, these cold days are actually becoming less common. Their definition here again of cold days is how many of the days are colder than 90% of the days in the past were. Okay? So you've got a whole long list of March 16ths. You know there's a certain temperature that 10% of the time it was colder than that. How often does that happen in the future? And again, if there was no climate change, this would be a stationary horizontal line across this graph right at 10%. We would expect 10% of the days to be colder than the 90% of the days. But that isn't the case in the future, regardless of whether we're talking just a moderate amount of climate forcing or a very large amount of radiative forcing on the climate. If you have, to keep the lecture a little shorter, let's just focus on the red curve here. At 8.5 watts per square meter of radiative forcing from anthropogenic sources, only about 1% of the days in the future will be as cold as those coldest 10% of the days in the past. Cold days start becoming very rare, about 10 times less common as they are now. Excuse me. Wow. So, alright, so, just to take some verbiage right out of the IPCC report. In summary, it is very likely, again, very likely is a term they have defined someplace in the margins of the book or at the footnotes or something. I can't remember, I didn't write it down this time. I think it's more than 90% chance that anthropogenic warming of surface air temperature over the next few decades will proceed more rapidly over land areas than over oceans. That's a good thing to know. And that warming over the Arctic in the winter will be greater than the global mean warming over the same time period. In other words, the Arctic is where we expect the very most amount of warming, particularly in the winter. Alright. I'm not going to worry about the second half of that paragraph there. Everything I've shown you so far has been at the surface. And in fact, almost all climate change research is at the surface because the climate system is complicated. We need to make sure we understand the parts where we live and where environments that we live in are and the creatures we depend on are and so on. But what if we were talking about climate change away from the surface of the Earth? Well, I wanted to just throw this verbiage out because it's got a key vocabulary word we need to spend a little time on. It says changes in the zonal mean temperature. I don't know what that word zonal means. We'll come back to that. Changes in zonal mean temperature for the near time period, that is out to the year 2015 compared to the base time period, in these model ensembles show a similar pattern to previous model examples with warming in the troposphere and cooling in the stratosphere and so on. The result there isn't so important as what's up with this word mean, zonal mean temperature? Zonal. Zonal is an old, crusty, creepy word that atmospheric scientists like to use. Zonal in this sense means east to west. The average temperature from east to west. In this context, just to give you a sense here, by the way, another example of the word zonal or zone in meteorology. You're all survivors, I think, of the 113 Introduction to Meteorology class. You might remember the Intertropical Convergence zone, that band of thunderstorms that goes from east to west around the world near the equator. That's another example of the word zone here. In this case, zonal mean, or zonally averaged, or whatever, means that we have computed the average temperature along a particular latitude all the way around the world. So, like, what is the average temperature at 30 degrees north, or what is the average temperature at 60 degrees north? Let me illustrate that for you for a moment. I was playing around with a website that lets me make climate research type plots, and I just made, I don't know why I chose January 2009. This is temperature, happens to be near surface temperature. It's actually the 1,000 millibar temperature. In other words, the temperature at the height above the ground where the pressure is 1,000 millibars. Most places on Earth, this is very close to the surface of the Earth. That's not what's important here. It's a map of near surface temperatures as it happens for January 2009. Every location on this map, there is a temperature associated with it. There's data here. And we have analyzed it in such a way to make a pretty map of it. Okay? Now, I could take those values and like pull out just the ones that are along a particular latitude line. Like maybe 30 degrees north. Okay? I've got the 30 degrees north latitude line indicated right there. And I could take all those values and take their average. And if I looked at this plot right here, that's what I did. I actually loaded these values that made the plot be in the background there into an Excel spreadsheet, took an average of all the ones along 30 degrees north, and that's this spot right here that I have indicated in red. Along 30 degrees north, you can see that on the x-axis there, I have zonally averaged all of the temperatures along that latitude line, and I came up with, I don't know, what is it, about 15 degrees Celsius at that time. Okay? And then I could do the same calculation again and again for different latitudes. For example, I could do 60 degrees north. I could pull all the observations out of 60 degrees north in my little Excel spreadsheet there, take their average, and I found that at along 60 degrees north, you can see that along the x-axis here, you can read up, and the average temperature in Celsius there was about 11 degrees below 0 Celsius. And you can in fact do that for every point at every latitude, and that's where they constructed this curve, where you can see that, like, for example, at this particular time, because it's January, it's not terribly surprising, that it's colder up near the North Pole and it's warmer near the South Pole. Of course, it's warmest around the equator, and you can see how temperatures change with respect to latitude and so on. Zonally average statistics like this can be really useful, and you're going to see some examples of that in the third module of the course. I'm sorry, the third part of this lecture. So the right vocabulary word here is to say that we have zonally averaged. This is a plot, this little Excel chart that I have superimposed on here, is a zonally averaged, it's a plot of zonally averaged temperature. In particular, at a particular level, this is 1,000 millibar level, particular height above the ground, and at a particular time, this is in January of 2009. It's actually averaged across all of January 2009. And as you're going to see, curves like this are actually a really important tool in climate science. For that matter, we could have done it for all the levels and then made it on a plot like this. This would be a zonal mean cross-section of temperature in January 2009, where, like, again, we have latitude across the x-axis, and we now have height on the y-axis. It's actually measured again in terms of pressure, so it goes from like 1,000 millibars at the surface up to about 100 millibars aloft. So, like, for example, that plot that I made you before that had that Excel graph, that I just made in Excel here, this curve right here that I made, that corresponds to the values along this red line right here. This is the 1,000 millibar zonally average temperatures. So, like, if I picked off the value here at 90 south, that should be this value right here. And if I picked off the value at the equator, that should be this value up here, and so on. I've just made lots of these zonal mean curves, and then I plotted them in such pretty colors. This is a really powerful tool, and we're going to, even in the third part of this lecture, going to be using this quite a bit. And it will be useful for us to have a little bit of notation here. These plots were all about temperature, T. and then there's also going to be T-bars, and there's going to be T-bar brackets. What do we mean by that? T, just by itself, is the variable temperature. But when you just have T like that, you mean the temperature at a particular location, you know, like some latitude, some longitude, and some height, at a particular time. That's kind of a four-dimensional depiction of temperature, right? At a particular latitude, at a particular longitude, at a particular time, at a particular height, that's the temperature. That's in contrast to T-bar. Now, most people know that the bar, over bar like that, means average. But in particular, in meteorology, when we label something with a bar like that, we mean the average over a period of time. So like those maps that I showed you of the average temperature in January 2009, that's T-bar. Every latitude and every longitude still has a value, and that value at that location is the average temperature over some defined period of time, like over the course of the month of January 2009. In contrast, then, there's also brackets. Now, that might be new to you, but statisticians and climate scientists and a couple other contexts too also can use the square brackets to mean average. And in climate science, we use those square brackets to specifically mean the zonal mean average. So like T-bar bracket means that this is the zonally mean average. So we have averaged along a latitude line. And the bar, of course, means that this was already averaged over time. So like, for example, this plot that I showed you at the beginning of this little block of information right here, that was T. I'm sorry, no, that was T-bar. Because that was January 2009. A whole bunch of data at each of these points went into that plot. You know, the temperatures every hour for a 31-day period went into that. So every location on here has a value that is the average over a period of time. That's T-bar. Okay. Whereas like this curve that I made from that data in Excel, that would be T-bar bracket. Because it's based on time average data, averaged over the month of January 2009, and then take that data and average along each latitude line all the way around the world to get this graph. It's T-bar bracket. Again, we're going to be using this bars and brackets type notations in the third part of this lecture and elsewhere in the course. For that matter, by the way, this cross-section of the zonally averaged cross-section like this would also be denoted as like a T-bar bracket here. This can be kind of a difficult idea, and what we're going to do is we're going to answer a bunch of questions right now, more than we usually do between two sections of a lecture. And after that, if you have questions about this would be good information to go get, you know, some help from me. Get a hold of me by phone, by text, by email, whatever, Google Hangouts, whatever works for you. Because it is kind of an important notation. Now, you'll also see more about it in the third part of this lecture, but let's get it sorted out. Let's actually talk a little bit about climate change in general first. Question 4. Between now and the middle of the 21st century, the greatest warming at the surface of the Earth is expected to occur, A, at the mid-latitudes of the Northern Hemisphere, B, in the tropics, or C, in the Arctic. Where are we expecting the biggest temperature changes to happen at the surface of the Earth? Make a choice from those three options and get a little feedback before you move on to question 5.